Greetings to everyone. My name is Giorgios Vlachakis, and I am a PhD student at the University of Minho working in the Stanford Heritage Project. In the MATICH cluster of ICISE, we study masonry structures since they constitute an important portion of our built heritage. Nevertheless, masonry structures are particularly vulnerable to earthquakes. During a seismic event, cracks develop, forming in-plane and out-of-plane mechanisms. The in-plane mechanisms occur when there is a box-like behavior of the structure, and they are a preferable type of failure since the capacity of the whole structure is mobilized. On the contrary, out-of-plane mechanisms occur when there are connections among the structural elements are insufficient, thus resulting in destructive collapses. Importantly, these mechanisms are the weakest, and at the same time, their behavior is the least understood in the scientific literature. Therefore, within the Stanford Heritage Project, we try to analyze the dynamic behavior of these mechanisms using both experimental and numerical techniques. The experimental campaign is based on the shaking table that was recently installed in the laboratory of the university. On top of the shaking table, we construct and test specimens that replicate out-of-plane mechanisms, such as the rocking response of a facade using a rocking block, or the vertical spanning wall with a restraint on top. Moreover, we record the complete three-dimensional motion of the specimens using a digital image correlation system of 6 cameras, which surround the shaking table. As a result, we are able to reconstruct the 3D motion of our specimens, study their dynamic response, the impacts that occur between the blocks, the energy losses and damping phenomena, and of course their collapse. Furthermore, since we are using dry joint masonry, we are able to perform hundreds of tests in a reasonable time, and thus have a statistical view of the results. For example, for the previous 2 mechanisms, we have already conducted more than 1,000 tests in the last 2 years. Finally, we also work on the development of numerical models in order to predict the out-of-plane dynamic response. These include both analytical rocking dynamics, but also advanced finite element techniques. More specifically, for the specimens that include few degrees of freedom, we can create analytical models by writing and solving the equation of motion using rocking dynamics. These models are fast and accurate, but work well under certain assumptions. Moreover, these models are practical only for simple 2-dimensional mechanisms with few degrees of freedom. On the contrary, advanced block-based finite element models are more powerful in replicating 3-dimensional geometries with many degrees of freedom or complex boundary conditions. Here, we are trying to improve the constitutive laws of these models, and especially their dynamic contribution, which rely on nonlinear damping models. Finally, the performance of all the numerical models is tested against the experimental outcomes. For more details on our research, please visit our website. Thank you for your attention.